Hi, everyone. Let's continue on with Chapter 10. So let's say that you're standing at a palm tree at the origin here. You dig underneath the tree and you find some instructions, a treasure map, that are meant to take you to a point out in the sand where you can dig and get concert tickets for your favorite musical band once we're after this whole mess with the virus. So here's the question for you. What instructions can get you from the origin over to this point over here? What are some examples of pairs of bits of information that the treasure map could give you to get you from the point at the origin to this point over here where the tickets are? Well, the treasure map could give you instructions such as go 3 meters east and 4 meters north, something like that. In which case, the treasure map would be giving you Cartesian or rectangular information, and basically the coordinates of this point would be 3, 4. That's a Cartesian way of looking at things. But is there another pair of bits of information that could get you from the origin to the tickets? How about this? If the treasure map tells you how far to go to get from the origin to the tickets over here, so it tells you to walk 5 meters, for example, and if the treasure map tells you what else? Because, hey, I mean, well, 5 meters, do I go this way, this way, this way? Which way do I go? A direction, like maybe a direction angle, right? A direction angle, which we often denote by theta. Theta could represent a direction angle. The distance from the origin to this point here, we can call r, a polar coordinate for this point. In fact, r and theta represent polar coordinates for this point over here. And that's going to be our topic for today. Polar coordinates. All right. Now, we saw this stuff back in section 6.3 when we were talking about vectors. So look here. We have here a vector v, and we're looking at its position vector representation, where the initial point is at the origin, and the terminal point is the point a comma b, or x comma y. Let's say that this vector is x comma y, all right, and we can represent it as this position vector from 0, 0 to x comma y. A and b are like specific values. All right. Now, we can associate the length of this vector with this notation, or we can just call it r. R is the length of this position vector. It's the distance from the origin, or pole. We can now call this point the pole. The distance between the pole and this point, a comma b or x comma y. And you may remember from section 6.3 that there is a cosine relationship between x and r, and there's a sine relationship between y and r. So from these relationships, we get this, that if you convert from polar to Cartesian, all right, the x-coordinate is r cosine of theta, the y-coordinate is r sine of theta. The coordinates of this point. In other words, the components of this vector. X equals r cosine of theta, y equals r sine of theta. And often in Calculus 2, Math 151, you go from Cartesian to polar. You actually replace x with r cosine of theta and y with r sine of theta. By the way, notice that from the Pythagorean identities, we get that x squared plus y squared equals r squared, which corresponds to the Pythagorean theorem applied to this triangle here. X squared plus y squared equals r squared. That's used very often to relate this polar coordinate with these Cartesian coordinates. All right, so let's talk more about polar coordinates. So imagine that you have a point here in the plane, all right, the point P. And instead of indicating Cartesian or rectangular coordinates, x and y, let's indicate polar coordinates, r and theta. By the way, it's not conventional to put these in parentheses the way we do with x and y. So I'm not saying that r always comes first and that theta always comes second, but that's the idea, that we can associate a pair of coordinates with this point. An r coordinate, which is the signed distance from the pole, and a theta coordinate, which is the direction angle. A theta is usually assumed to be in radians. All right. Now, notice I said that r is the signed distance between the point and the origin or pole here. Now, if r is non-negative, then this direction angle is as usual. But the thing that's kind of funny is that even though in section 6.3, we assume that lengths, like lengths of vectors, were always non-negative, actually, when you consider polar coordinates, r can be negative. It is legal for r to be negative. That's okay. If r is negative, you're actually walking in the opposite direction from what you expect. We'll talk more about this later on. Also, the positive or non-negative x-axis is now called the polar axis. This corresponds to theta equals 0 for non-negative values of r. Okay, now let's talk about some basic graphs using polar coordinates. Let's go to Desmos. All right, so let's think about this. In the Cartesian or rectangular plane here, right, how do we get these grid lines? Well, we have on our grid paper here, we have things like x equals 0, which is the y-axis. We have x equals 1 over here, x equals 2 over here, and we have grid lines lying on these vertical lines. We also have y equals 0, the x-axis, y equals 1 up here, y equals 2 up here. And of course, we could have y equals pi, y equals 4.7, y equals negative numbers, all right? But the idea is that when you draw a Cartesian graph paper, you have vertical lines that corresponds to x equals a number, and you have horizontal lines corresponding to y equals a number, right? Vertical lines, like these guys, x equals a number. Horizontal lines, like these guys, y equals a number, where the variable equals a constant number. So now what does polar graph paper look like? And I have this on the homework set, you'll see. And you could be given this on homework exams. So here in Desmos, notice I clicked on the wrench here. Under grid, if we go from the Cartesian grid over here to the polar grid, this is polar graph paper. Now, what's going on here? All right, now, how do we graph r equals 1? How do we graph r equals 1? And here's a clue. Remember the basic principle of graphing. The basic principle of graphing. The graph of an equation consists of all points whose coordinates satisfy the equation. The graph of an equation consists of all points whose coordinates satisfy the equation. Back in the old Cartesian or rectangular days, you took this for granted. Let's go back again to the Cartesian grid. All right. How do you graph x equals 0? How do you graph x equals 0? It was the y-axis in blue here. Why is that? Because it contains all points, it consists of all points with x coordinate 0. 0, 0, 0, 1, 0, 0.865, all these guys, right? Okay, 0, 1, right? 0, 2, or 2.02, 0, pi, 0, negative 1.58, whatever, all right? The graph of an equation consists of all points that satisfy the equation. In this case, all points with the x coordinate 0. But now, what if we go to the polar graph paper? How do you graph r equals 1? What are all the points that have r coordinate 1? The treasure map says r equals 1. The tickets are 1 meter away from where you're standing. what would be your search path? What figure would you trace out with your shovel? R equals 1, that's going to be the unit circle. If the treasure map says the tickets are 1 meter away, then the search path is potentially along this entire unit circle. How about R equals 2? That's a circle of radius 2, centered at the origin or pole. R equals 3, circle of radius 3, centered at the origin or pole. So R equals a constant number, all right? They're going to correspond to circles centered at the origin or pole. What about R equals 0? R equals 0 just corresponds to the dot right here at the origin or pole. Okay, I guess you can't click on points here for coordinates. R equals 0 corresponds to the origin or pole. There's only one point with R coordinate 0, right there. All right. Now, likewise, what if we wanted to consider, before we do that, what about R equals -1? Can Desmos do that? R equals -1. No, Desmos doesn't know this. Actually, R equals -1 has the same graph as R equals 1. It's just that you're looking at the angles from a different perspective. We'll talk about that later. So R equals 1 and R equals -1 have the same graph. We'll talk about that. Now, what about theta equals pi over 4, let's say? Theta equals pi over 4. Now, Desmos doesn't know how to graph that, but you should. The treasure map says, from the origin, the pole, where you're standing, the tickets are at a direction angle of pi over 4 or 45 degrees away from where you're standing. What would be your search path? Now, technically, it would be on a ray. Here's pi over 4. Technically, it would be on a ray, like so. R equals 0 here, R equals 1/2, R equals 1, R equals 2, R equals 3, R equals pi, and so forth. But actually, if you allow R to be negative, and we do, we actually include the whole line that goes to the origin or pole. So theta equals pi over 4, the graph of that is a line. Okay. For theta equals pi over 3, okay, for theta equals pi over 3, for theta equals pi over 3, it would be along here and along here. I'm not drawing it very well, but pi over 3 and also the 4 pi over 3 ray. Remember, these correspond to negative values of R if you let theta be pi over 3. We'll talk about that. Now, by the way, if you wanted to graph these in Cartesian coordinates, okay, let's go back to the Cartesian grid. Right. So theta equals pi over 3, or how about theta equals pi over 4 first, okay? That corresponds to y equals x. Here's the graph of theta equals pi over 4. It's actually graphable if you use Cartesian coordinates, y equals x, right? For all the points here, theta equals pi over 4. Over here, r is 0 at the pole. Over here, r is negative in quadrant 3. You're walking in the opposite direction from where you'd normally go. For theta equals pi over 3, remember, folks, tangent is slope. The slope is the tangent of pi over 3, the square root of 3, all times x. That's the graph of theta equals pi over 3. R is 0 here, R is positive here in quadrant 1, R is negative here in quadrant 3, the opposing quadrant. So what's this idea of R being negative? We're going to talk about that in the next video.